Okay, welcome to our October Quant Stew meeting. Quant Stew is an informal study group we started over the summer as a way to help learn more, most importantly, but also give us a chance to present our own work and present some of the stuff that we've been working on. A very good way to develop experience and build a resume is to replicate papers or explore a new topic. And the topic we have today is a very important one. Market regime classification, and Jack has done some interesting work in a way to apply machine learning to that. I'm going to introduce Chenyang Gu. Jack is a master's student at NYU's Courant Institute, one of the top-ranked MFE programs in the world. Courant Institute in particular is one of the leading applied math centers around. So very, very high-powered faculty and very clearly high-powered students. So without further ado, I'll hand it off to Jack, and please take us through what we can learn about today.
Sure. Thank you, Matthew. Good morning and good evening if you're in Asia. Thank you for coming. First, I would like to introduce myself a little bit. Matthew had talked about it, but yeah, before coming to NYU, I had one year of work experience as a quantitative researcher, where my focus is equity modeling and the algorithmic organization, like machine learning, and the automation of such models. Since we have a small audience, I think you can just ask any questions if you have, and then we can give you a very timely response. So today, I would like to introduce a model called Variational Auto-Encoders and introduce its application in market regime classification. We'll talk about it later, but just to give you an idea about what market regime classification is, just imagine you have a lot of strategies and you want to filter out several that could use for now, and the rest of them may be limited to the computational resources. You want to put them aside and use them later. Well, that is why the market regime classification comes into practice. Okay, so here I would like to give you a more formal motivation of why we would like to use such a model. First, if you do equity model, you know that the alpha actually disappears. I would like to refer to an idea mentioned by Claire Levy in the talk. The alpha life cycle actually is defined by how the portfolio manager constructs the alpha at the beginning of the portfolio design, and when he uses it, the alpha actually fades out. And as you see, many strategies may start with a very great positive return, but generally they fail and cause losses that just wipe out all the prior earnings. This gives us the idea of smart beta, which is originally theorized by Harry Markowitz. We know his theory called the modern portfolio theory, which tries to use factors or smart betas to explain the risk factors that could bring about returns in the market. And this soon boasts popularity because it is very concise, and most importantly, it has a theoretical basis. And this is why companies are investing a lot on finding effective beta factors. And in the States, we have barrier factors, and in China, we have a lot of companies who try to find out a lot of factors to build up their own factor model. But as a result, many companies nowadays have a very large factor library, maybe comprised of thousands or even millions of factors. Some are constructed by hand, and the rest of them are constructed by machine learning or other models. But this gives a practical challenge that very complex factors actually incur very heavy computational costs. And we want to find out a strategy to optimize this process. We don't want to invest a lot of money buying GPUs and fast computers to compute all the factors. So is there a strategy that we can quickly filter out some factors and to focus on only a fraction of the factors? So this is where we introduce the meta strategy which is a strategy of factors. We want to assign priorities to factors. Maybe it's a weight, or maybe it's just we want to wipe out or eliminate some factors and to put off the usage into the future. We want to target as available resources. Maybe it's the GPU, maybe it's computers with a soft constraint. We don't just want to say, okay, we have enough factors, we don't want to get more. I don't think it's realistic, but if we have such a strategy, we can still expand our factor library. We can still hire people or use machines to find more smart betas or factors. And they can be still useful, and yet we can improve the performance immediately without additional resources, and we can put them into use if we already have additional resources. I'm sorry, I need to hide this. Sorry, okay. Okay, the problem is how to score each factor. If we want to set priorities, we need a strategy to score them. So here I'd like to introduce, maybe we can do some brainstorming and find out some key objectives we want to know about the scoring. Maybe it should be independent of the factors. If we already know the factors, which incur a lot of computational costs, then maybe we don't need such a metric to score them. So, and again, we want it to be able to self-adapt as different market regimes. And this is why the market regime comes into our realm. That is because we want to know whether this factor is still useful at this time. And we want to know how it compares with that time when this factor is constructed. We also want this factor scoring to be easy to optimize and easy to reconstruct. And maybe we want to account for some randomness. We know the market is full of randomness. And the traditional machine learning is just do not account for randomness into the construction of the model. So if there are any model or any strategy that we can use to account for that randomness, the first two objectives are quite generic, which we will cover first, and the rest of the are quite model specific. And we would like to introduce it to introduce a model called Variational Auto-Encoders to solve the rest two objectives.
Excuse me, Jack.
Okay, then let's start with
Jack, just a couple of questions on factor scoring. When you say factor score,
sure.
Are you referring to the efficacy of the factor itself? That is to say, some sort of t-stat to determine whether it's a meaningful factor, or do you mean the some level of the factor at a given point in time? Like, is it a factor return that you're quantifying? Like, what do you mean by score? I'm sorry, I'm not quite understanding that.
Yeah, sure. I think the first understanding is correct. We want to assign a weight to a factor, but this is rather we don't evaluate the factor itself. We want to evaluate how effective is this factor at this time, at the present, compared with the time that the factor is constructed. So sometimes the factor is constructed in the past and it works well for maybe for years, but we don't know how it works today or maybe in the near future. So that is how scoring comes into our realm.
Okay, and so like we can look at the current market environment where value has dramatically underperformed, and we could say that value would have a very low score, and momentum, which has done really well, that is like the Facebook's, Netflix, the stocks that are doing well tend to keep doing well. And so momentum, if it was a factor, would have a high score in your definition. Is that a good way to think of it?
That is one way to think of it, but I would keep it quite more generic. That is, if the market today is different from the market in the past, all we can say is that the market is different. So the factors may not have the same accountability or the same effectiveness as it was years ago.
And then,
so
when we say
if we know a certain,
please, I didn't mean to interrupt.
Sorry, and we don't want to constrain the factor into a few companies like Facebook. We want to evaluate this score using even the full market data to know whether the market today is different or how similar it is from that in the past. That is scoring. I would say factor scoring is not the score of this factor, but it rather refers to the score of the market between today and that in the past when the factor is constructed.
So the right way to think of it is in terms of like a smart beta factor definition, which is some collection of securities. This is the factor that we care about, not the mapping of the factor to the individual securities. That's the level of resolution we're at.
Yes, yeah.
Okay. And one final clarification. What do we mean when we say a good score should be independent of the factor itself? That means that the level of the factor can go up and down, but the score should not go up and down as the factor goes up and down?
Here is just a proposed some objective we want to optimize. Maybe we can have a different interpretation of this factor scoring, but here I would like to propose my understanding. And I admit that it's there are a lot of ways to build models to account for the different market regimes.
You're giving me too much.
Factor scoring is just one of them.
You're giving me too much credit. I wasn't criticizing the point. I'm just trying to understand what you mean by a good score should be independent of the factor itself. Like, seems like an important point, but I'm not understanding it.
Maybe we can just go on and see whether the following pages can explain it. Okay, great, thanks. So the generic objectives, the first we want the factors. We know that factors are tested on diverse time intervals. Some factors may be tested 10 years ago, some may be tested 3 years ago. But all we want to invest in the future. We don't invest in the past. And also, a perfect factor should be effective to reflect on today's market, not the market in the past. Usually, we assume that the factor can work even today, even in the near future, but this is not always the case. And again, a bad factor may, but not necessarily, be obsolete or unable to match today's market. So I know there's a lot of solutions, but one solution I would like to propose today is we want to compare the market regimes between when the factor is constructed and the market regime today. And we can model this difference with using a distance between the latent states variables, which is very common in dimensionality reductions, where we want to squeeze the high dimensional data into a lower dimensional data, where we extract the latent variables under some certain metric. So here is a graph for that. We want to construct a score, and this score, as I would define it, is a difference between the latent variables when the factor is constructed and the latent variable today. And the latent variables are constructed with another function that maps the market variables into a smaller subset or subspace of the real numbers or the states. And here the score, again, maybe you can have different interpretations. You can score the differences between different markets, even if you want to account for the factor itself. But just out of simplicity, here I would like to omit what the factor is talking about and only focus on the different markets. As you can see, we only construct the latent variables from market variables, and we don't use the factor itself to construct the score of the factor. Okay, next we want to choose an encoder, which is the F that maps a market variable into a latent space. We want to estimate an encoding function, but how do we do that? We know that in deep learning, we have a lot of methods. We have backpropagation, which is straightforward to use. Maybe it's not the most accurate way to model the encoder, but it is instructive and usually easier to optimize. And also, the latent variable is unknown a priori. We don't know the latent variable only from the data, so we cannot fit them directly. That is, in other words, supervised learning will not work here. That is why we want to use unsupervised learning instead. And autoencoders is just one such method to squeeze information into a lower dimensional latent variable, which we can also easily reconstruct the input data. We will see a diagram for this model later, but just to give you an intuition, we attempt to reconstruct the input with a decoder, and we optimize the differences between the input and the reconstruction using backpropagation, which is a common strategy in machine learning. And in practice, both the encoders and decoders consist of linear layers and the activation functions. So I would like to assume that you already know some machine learning techniques. So, if so, I believe you can understand how this model works. We have the input, and we have F, which is the encoder. We map the input into a latent space, and then we decode it using linear layers, but the dimension is increasing until finally we get the reconstruction with the same dimension of the input data. And we only need to compute the differences, maybe the mean square error between the input and the reconstruction, and use backpropagation to optimize the parameters. So far, do you have any questions about autoencoders or the specification of the model? Okay, great. If you have any questions, just raise your hand and just unmute and say, because I think we have a smaller size of group. So yeah. Okay, so far we talked about the autoencoding, but now we want to introduce how to solve the last objective, which is the randomness. The traditional autoencoders, as we see, do not account for randomness. We just squeeze information and expand. You don't see any randomness in that. And this may incur overfitting. Even if there is no overfitting, the model is also not correct, because we know that in the market we have intrinsic randomness. So it is very important to actually account for that randomness into our model. And one strategy to solve this is to use variational inference. So what is variational inference? Instead of fitting an encoder and a decoder, we want to fit a distribution of the latent variable instead. Equivalently, we want to construct the posterior distribution based on the data. We can sample from the distribution and obtain the latent variable. And the rest part of the model can just remain the same. We use the input with the encoder to generate the distribution, and we sample from the distribution. And we use a decoder to recover the input, the market variables, using use a decoder, and in this way we replace the decoder with exactly the same one as we saw before in the autoencoder. If you want to learn about the variational inference from another perspective, which is a sampling perspective, you can see the post. I will distribute this lecture note to you after our presentation, so you can just click here and see the post. Here is the assumptions about variational autoencoders. So some same assumptions as the traditional autoencoder is that we need an encoder and a decoder, as we talked about previously, and we want to fit the reconstruction to match the input, but we need additional assumptions. The first which is very important, is that we need a family of distribution. We don't just fit any distribution, which is very difficult. Instead, we want to fit maybe a parameterized Gaussian distribution. In other words, we assume that the latent variable is sampled from a Gaussian distribution, and the latent variables are sampled from that. The Gaussian distribution is simply parameterized by the mean and the variance. We can even simplify this by specifying the mean values and only diagonal elements of the covariance matrix. That is to say, we assume the interdependence between different elements. And then with the encoder to fit the input into the parameters. And within parameters, we know the distribution and we can sample from it. Sampling from a Gaussian distribution can be easy. And after that, we get the latent variable and use a decoder to recover the input. We also need a new loss function. This is not quite intuitive. Mean square error just fails in this situation. And I would like to tell you why. Because MSE fails because our objective has changed. We want to rather to fit a distribution instead of the model itself. So MSE simply doesn't match this objective. And also MSE simply ignores the increased degrees of freedom. Now we have more degrees of freedom. We have more elements to fit. So in the past, we have an encoder and a decoder, but now we only have a sampling engine in the middle of the model, which increases the degree of freedom. And this may also incur overfitting. And here, I know that in the literature, we have a lot of loss functions for this purpose, but the most straightforward one is the Kullback-Leibler divergence, or KL divergence for short. This is, I believe, the first loss function proposed, I think it's in 2014, when the authors designed the variational auto-encoders. It is a measure to estimate the differences between distributions. And here we have the definition, which is simply an integration. But this is hard to use, so we'll see how to apply this to real data. Here are some basic properties. We know this is not negative. The KL divergence is usually always positive, and the equality holds if and only if the two distributions are identical, which is great. So we can minimize this KL divergence in the hopes that we can find out a best distribution that accounts for the latent variables. It is also convex, so we don't need to worry about the result of the optimization. We always get the minimized value after the model converges. Also, we have a not quite good property of this KL divergence. This is not communicative. The KL divergence between P and Q is simply not the divergence between Q and P. And this gives you a real problem. We want to know the difference between the likelihood and the parameterized distribution. But which one should be P? Which one should be Q? We see the order really matters. The likelihood, as the answer, here's the answer. The likelihood must be the right term. And here we have a post that gives you an explanation. Here is just an intuition for you, is that if you admit a partially correct model is always better than a totally wrong one, then maybe you can figure out why we should put the likelihood as the right term, and we should put our reconstructed parameterized distribution as the left term. Okay. Now, I would also like to introduce a new idea called evidence lower bound, which is exactly the KL divergence. But as we saw before, the KL divergence is integration, which is hard to compute. So is there any substitutions that can be computed easily? And yes, we have. To minimize this KL divergence, we are literally maximizing the log likelihood minus the KI divergence between the reconstructed parameterized distribution and our prior. As you see, the right-hand side is much easier to optimize because we know the log likelihood is simply a product of our observations, and the KI divergence between Q and P. If Q is Gaussian and our prior is also Gaussian, then the second term is actually solvable in a closed form. Here I have a link that gives a proof, but intuitively this is very easy to compute. And also the log likelihood is even simpler because it is if you do some math and assume the prior being a Gaussian distribution, it is simply the traditional MSE. So as you can see, this is very easily implemented if you use, yeah.
Jack, how sensitive is this approach to the assumption that our prior is Gaussian? For example, maybe it's exponential.
Yeah, if you
right?
admit, sure.
You got it.
Yeah, it's exponential, yeah. If you admit it's Gaussian, then everything can be very simple. But usually we can also use a uniform distribution, which is very common. But the rest of the distributions, more complex ones, they can add to some difficulties when optimizing this evidence lower bound. So just practically, we want to use the Gaussian prior, but it's not the only option, I would say. Okay, yeah. So to sum up our structure of this variational autoencoder, so I lost the, I forgot the word here, it should be the variational autoencoder. We have input, and the encoder gives us the latent distribution, which is, you can just imagine it as some parameters to a Gaussian distribution. And we sample from a distribution to get a latent realization. And finally, we use a decoder to reconstruct the input variables. And the elbow, or the evidence lower bound, tells us how to evaluate the differences between the input and the output. So we can use you can use any machine learning library to optimize the whole model. Next, I would like to introduce some details of this model. The first is what distribution to use. I mentioned the Gaussian one, but can we use just any other distribution for the latent distribution? And maybe if we use a parameterized one, then things can be easier because we only need to fit the parameters. It's also easy, as we see, it has a closed form for the KI divergence between the distribution and the prior distribution. But if you want to use more complicated latent distributions, you could use normalizing flows. And the normalizing flows is simply a technique to use a bijection to map a Gaussian into any distribution you want. So it is the linear models or the spectrals of the distributions. I think this technology is quite new. It was put forward in, I think, 2016 or 2017, and it's quite new here. Simplicity. And next, we want to do backpropagation with sampling, which cannot be traced. The derivatives cannot be traced through the sampler. It is quite difficult to implement. You see, we have an encoder and we have a sampling process and then a decoder. But how do we backpropagate the derivatives through the sampling process? We can't imagine it. And in fact, we cannot do that. And we need a solution for that, which is called the reparameterization. Sorry. The reparameterization is simply a technique to sample from another distribution, a more standard one. And in the hope that we can recover the latent realization using both the latent distribution parameters and the sample from a more standard distribution. And here is the model. and we see the differences between this one and the one I just proposed. We still have the input and the encoder, and we get the parameters of this latent distribution, which is mu and we talked about just now. We still have the input, the encoder, and when we get the parameters of this latent distribution, which is mu and sigma, we don't simply sample from it. Instead, we sample from a normal Gaussian generator. We get the epsilon from it. And then we use this formula here, the mu plus the Hardeman product of sigma and epsilon. The Hardeman product is simply the element-wise product. So if you have two n-dimensional vectors, you multiply element-wise to get another n-dimensional vector. And this is the realization of this latent variable. And finally, we use a decoder again to reconstruct the input variables. And again, we use the evidence lower bound, or equivalently, we use the minimization of the KL divergence to do backpropagation through this whole model. Okay, I think we've through everything. Now I would like to give you a demo to as how I implement this with PyTorch and visualize the results with matplotlib animation. Okay, let's see. Okay, here is my Jupyter notebook. Let's start from the data pre-processing. The data pre-processing. The data is daily close price of the stocks, which is adjusted due to the dividends and the split of stocks. And we calculate the 10-day return rate, which is equivalently the 2 weeks, the biweekly return rate. And we drop the data a bit before 2014, and then we drop the null values. We use the data from 2015 to 2019 April as a training set, and use the rest of them. So I only have data until the mid-year to 2019. So here I only use the data from May to June. They only have data until June 2019, so that's what I use. The training part is from 2015 to 2019 April, and then I use the rest of 2 months as the validating set. As you see, we have 1,054 observations and 39 as a validation set. And here is some values in the matrix. Remember, this is a 10-day return rate. And each row is an observation, and each column corresponds to a security or a company.
So I notice your data appears
standard.
Jack, sorry. Notice your data appears to be advancing daily. If you scroll up, please, to the we're looking at January 5th, 2015, January 6th. So those returns are the 10-day trailing returns of the stock as of each day.
Yeah, the 10-day. Yeah.
Okay, so it's like
each entry is a 10-day or bi-weekly return, but it's daily observations.
So there's some overlap between the daily observations.
Yeah, exactly.
Okay, cool.
Okay, great. And the specifications of the model, we can go to this line, which defines the model. And here is how I implement the model using PyTorch. Here's the encoder. We use a linear layer to squeeze the number of stocks, which is about 2,500, into a 256-dimensional vector. And we use a RELU layer to introduce some nonlinearity. And then we use a linear layer to squeeze it again, accompanied with a RELU layer. And then as where we diverge from the output. We try to squeeze the first. The first encoder is the mean value of the function, and the second one is the standard deviation, the covariance matrix of this the Ford function. First, we encode it, and then we get mu and the log variance, actually the log variance, because we don't want to have a negative. We want to fit the variance. The encoded x, but different. And next, here's a graph. Each point corresponds to the variance of each point, and the x-axis and y-axis are the mean of this point. As we see, we squeezed the more than 2,500 dimensions into a two-dimensional plane. That is the graph we get. And we also animated this. Here I use the animation library built in Matplotlib to get this animation. And we can see that here during the 2015, here, the May the 19th and the 20th, some points start to diverge from the line where most points gather. And these points start to walk around in a new place. So here actually is simply, if you are familiar with the Chinese stock market, this period actually corresponds to a stage where the market is soaring very fast and unstable. And after that, we see the points here. It's the end of June 2015. The points start to go very unusually to another direction. And this happens to be the great bear market of the Chinese stock market, where the stock index collapsed from around 5,500 down with a way to about 3,000. And that is a great catastrophe to the market. And here we see the market's going quite weird and fierce during the whole month before returning to the line where most points gather. So here. And another I would like to show you is this period. It's the beginning of 2016. It's another collapse. And the points here, we see they are traveling very far from, again, the place where most points gather. And we see before they return to the base. And this happens again in 2018, I think. It's not very clear here, but actually we could see around here, some points simply go a bit out here. So there should be reasons for this, why the points are not traveling so far like what we have seen in 2015 and 2016. But this model has actually at least proved effective to reflect and and you can see it somehow predicts the great collapse, just like we see here in 2015, because the market generally collapsed around the end of June, but this already start to go abnormal in the beginning of June.
What are the X and Y
if you only want
here?
to study how the X and Y are both the mean, because we want to squeeze the information into a two-dimensional Gaussian distribution, and each parameter is simply the mu is a factor, a two-element vector, X and Y. So both of them are the mu's.
So the mu's of what?
Yeah, the mu here, the mu for here is the two. The two here means the Gaussian, the latent distribution is a two-dimensional Gaussian. And here the x and the y simply corresponds to the two elements of that mean vector. Does that help?
Is one from the prior distribution and the other is from the?
No, they are both the posterior, but you know, it's the latent distribution is a multidimensional Gaussian distribution. It's multidimensional. It's actually here in this example, it's a two-dimensional Gaussian. And for two-dimensional Gaussian, it has two means in two dimensions. Yeah.
Got it. Thank you. Thank you. That's really helpful. So is it
great?
Is it useful to? So what we're concerned about is we have our lovely cluster in the middle, and when a little dot is away from a cluster, that means it's a different regime. Do we care whether these mu's are positive or negative? Does that have any significance, or is it more just distance from the original estimate?
It's actually the value of x and y does not quite matter. And in fact, if you rerun the training process, you get quite a different realization of this x and y. But what you have is that during some specific intervals, the points go quite far from where the points gather. But the distribution can be different. As we see, there are the variational part in the model. So it's reasonable to see that each training can be different. You cannot compare two models, but what you can compare is within one model, the x and y, the relative relationship between them can make sense.
Great, thank you.
Okay, I think that's all I can give. So do you have any questions about the model or the implementation or anything? I think we're quite stable here.
Does anyone, so anyone have questions they'd like to raise? Feel free to unmute and shout it out. And I think a lot of the benefit of the group is the discussion elements. In previous meetings, that's been where a lot of the interesting ideas have come out of. And clearly the presentation itself here is quite compelling. Just anyone has any, I do have a few. To get us started. In the beginning, you referred to smart beta factors and thinking about factor performance. Whereas here, when we're doing the, in your implementation, you identified, I think, 256 factors, but I think it was factors in the sense of like a principal component kind of factor. Not that you were using PCA, but that the factors are statistical factors, not identifiable or mappable to any kind of documented anomaly. And it was interesting. Do you see the potential? Is there a potential here to introduce some of the factor returns in terms of factors as they're defined in one part of the literature with like a value, momentum, equality, Fama French kind of factor framework?
I'm afraid we cannot model the specific factors. We cannot take into consideration the specific factors here in this model. And actually, I think maybe the wording of factor scoring is not proper here, because even in the implementation, I do not have any factors. I simply try to model the factors, the point is that for each factor, some factors have a specific explanatory reason here, but for some factors, maybe we don't have one. Like, I know is that many companies hire people or use machines to mine the factors, and they simply test the factors under some specific strategy in a fixed time interval. And they don't know the implementation, the interpretation of the factor. That is why I would say that if the company has a lot of factors, they do need a strategy to know whether this factor is still working. And here, this machine learning approach, the variational autoencoder, just gives this chance to eliminate the factors that are not simply working in today's market.
So the way to think of it is factors are pretty complex. What you're saying here is,
yeah, some factor can be. Yeah.
Go ahead.
So what we only care about is the differences between different markets or the different times of the market instead of the factor itself. That is why what I mean to score a factor. We actually score the time when the factor is constructed. We're not scoring the factor itself.
Cool. Okay.
Yeah.
So if I find a factor in 1982 and the factor in 1982 looks really good, what your approach here can say is, okay, here's I'm gonna not care about the factor that you identified in 1982, but I'm going to look at the overall market regime in 1982 and maybe the period you estimated your factor in, and then stepping forward, I can tell you how different the current environment is from the time when you developed your factor, and maybe you should reconsider your factor.
Exactly, yeah.
That's really cool.
Yes, exactly. And it's even better because we are only, here you see the image. The different market regimes are actually continuous. So you can actually calculate the differences between this market and that market. So traditionally we have classification. We only know, okay, we have maybe 3 or 4 different markets, but here we can actually know the actual distance.
And those distances have some measure of consistency across training. So if you reran this, would you expect similar magnitudes of distance?
Yes, it can. I would suggest a post I read earlier about autoencoders. It just tries to explain that the latent space is continuous. So if we have 2 points that are close, we know they are actually close when they get reconstructed.
Okay, great.
So that is any other non-variational models cannot achieve. But again, just like any machine learning model, you cannot say, it's quite hard to say whether this model is sufficient, because as you see here, I just squeeze the input into a 2-dimensional space, because I think it's very easy to display and to show here in the graph, in the planar graph. But maybe you can try this to squeeze them into a 4-dimensional, 5-dimensional, and definitely I cannot draw on my laptop. But the matrix here still makes sense.
Very cool.
Do you keep track of the historical? So as you're running these, so that if patterns reemerge again, to compare it, or that doesn't make sense? You're just looking at the present tense. Like you saw something in June in 2000, end of June, and then you said, oh, it happened again in 2018. So you're comparing like similar distances, but does it make sense to look at the previous patterns or just keep it current in the present tense?
They should make sense, but yeah, what we see here is that during this time in 2015, some points go very far from the middle point. They go to like the y equals 10, around 10, 15, but the points do not go back to those places again, which means that if we have some factors constructed during these very fierce market conditions, perhaps they are not going to be useful again.
Okay.
Because the market is kind of,
behaves differently, yeah. Okay.
Yeah, that's different. Okay. And in fact, you cannot only compare the market regimes between that day and today. We can just compare any 2 days. Any questions?
I had a minor one. I noticed for the 10-day rolling returns that you used, I imagine that gave a little bit more, it kind of probably smoothed out the returns that you were looking at. Are there any issues that you encountered with, I mean, that's absolutely going to introduce some sort of serial correlation because, you know, 9/10 of that is going to be on the previous 9 business days. So you're only advancing like 1/10 of the contribute, you know, assuming some sort of independence among returns. But if we do think that returns are actually independent, then we're only updating 1/10 of that information at every daily time step. Just be curious about, probably you looked at other windows or other approaches, and what were some of the logic between landing on that?
I probably wouldn't worry about the serial autocorrelation because in this model, if you are trying to model with a more classical like ARIMA model, then serial autocorrelation could be a problem. But here in machine learning models, I think it's quite common. I wouldn't say it absolutely makes sense because I haven't seen any paper that examine such thing, but since the training process actually views each observation independently, I would say that this overlapping could actually be helpful to better identify the continuous movement of the market regimes. And I actually also tried to use a daily return, and I cannot get such a clear and visible effects here. I see the points can go so far away from the middle point if you use the daily data. And I believe that is still a lot of things to study. I believe that if you use daily data, you should just simply increase the dimensions of the latent space. I think the 2 dimensions is not enough to explain everything here.
Yeah. Perfect. Okay, great. Thank you for that. And we'll also post we'll post the video to our newly launched YouTube channel for QuantStu. And
great. But I think I just guess maybe you need some to do some editing because we just experienced some technical issues repeatedly today.
Oh, I think that'll be part of the charm. So I don't. I've got papers right now, so I might be a little bit rough, but I'll see what I can cook up here. Maybe I should take that suggestion. So if there are no more questions, any final questions before we break? All right, Jack, thank you so much. This has been outstanding presentation. Learned a lot and appreciate your time and the effort to come share this with us.
Thank you.
Great, thank you too, Matthew.
Appreciate it.
Thank you, everyone.
Bye-bye.
Bye.